Hello, I'm delighted to see that the first lecture didn't discourage too many of you from coming back. Very encouraging for me anyway. Today we'll be talking about convolutional networks and techniques that are very much used in industry today. I'll speak for 1 hour, and then there'll be a seminar by Stéphane Mallat from the École Normale Supérieure, who will speak about the mathematical theories underlying convolutional networks. A very interesting work, I think. Probably one of the first research on theoretical matters linked to deep learning. Let me begin by ending what we were dealing with in the last lecture, to present issues linked specifically to convolutional networks. The techniques we spoke of regarding assembling blocks for deep learning so as to backpropagate gradients within the blocks don't apply strictly to the architectures we spoke of the last time, with blocks assembled sequentially in a stack, in a cascade. They can be arranged in any way, as long as the interconnection graphs have no loop. If the blocks have no loop, we can assign an index to each block so that the inputs of a block are always available for calculation. So there's a calculation order if the graph is oriented without any circuits. To calculate circuits from inputs, we use the reverse order to backpropagate gradients. In the previous phase, we calculated outputs from inputs, and vice versa. Sometimes we'd like to use networks with loops, also known as recurrent networks. Recurrent networks open up the door to many applications that could not be done otherwise. I won't speak a lot about them this time. Just like to show a small slide. There'll be a whole lecture on that, plus a seminar in the coming weeks. Before going any further, I have an announcement to make that I should probably repeat at the end. The time of our lecture will change because there's so many of you that would like to continue to use this amphitheater. Unfortunately, this auditorium is not available at this time in the coming weeks. So we'll be forced to shift the time of our lectures from 11 in the morning to 1 in the afternoon. So normally a lecture from 11 to 12 and a seminar from 12 to 1. That will be changed on the website, but I'd like to announce that since it will apply as of next week. There are a few practical issues linked to backpropagation that are important to know. Naturally, you can use any nonlinearity in neural networks. But recently, in the past, rather, we use hyperbolic tangents. And we realized that it generated problems. When the sigmoids are saturated, gradients become very small and the system doesn't work well, creating plateaus in the cost function that are very difficult to get rid of. In recent years, people focus more on using ReLU functions, a sort of acronym that means rectified linear unit. It's a demi-rectification, a semi-rectification, a function that was 0 when the argument is negative and an entity when the argument is positive. Very often, when you train networks in classification, you use a cost function that we call a cost entropy. It's a good idea for classification. It's a generalization for neural networks of the cost functions used in multinomial logistic regressions. A function that I spoke of the last time when talking about softmax and log softmax. And I spoke about the cost function of minus log softmax last time. It could be viewed as a measure of cost entropy of a desired probability at the output with respect to the distribution produced by the system on classes. As I said before, we use stochastic gradients, and very often they're used on mini batches. We spoke about that in the Q&A session, where you can group samples, we calculate all the outputs and all the states, we do backpropagation for each, and you average out the gradients for each sample before an update. This is not because of theory. There are no advantages to it, except that it makes the execution of neural networks much easier to parallelize on GPUs. It's hard to saturate GPU calculating capacity without using these mini batches. The size is 3032 on a GPU, up to about 1000 on a multi-parallel GPU. But the optimal is to use a batch size of 1 to truly accelerate learning, setting aside any material or hardware considerations. Of course, you must mix up the training examples. You can't have all the examples of one class and of another. The classes must be mixed up in stochastic gradients. Otherwise, the system cannot be trained for reasons that are easy to understand. It's a good idea to normalize input so that variables are more or less have a zero mean with a unit variance, let's say 1. One or another figure, but by convention you can choose 1. You have regularization techniques such as dropouts, which I explained briefly the last time, by Hinton and his group, a technique that consists, well, when you calculate a network, compute in a network, you compute as if a half of the units of a specific layer did not exist. So you take, well, this is implemented in Torch and elsewhere as an additional layer. Its role is at random for each sample to eliminate the output by about a half of the units in this layer. The reason for this is to regularize the system so that no particular unit is too important in decision taking, and the decision is taken in a distributed fashion. There's also a theoretical argument whereby the result of a dropout is that at the end, when you compute the entire output of the system without a dropout by using all the units, in a way, you have the output corresponding to the average of a very large number of neural networks where different subsets from the unit were eliminated, giving you a regularization that's quite good, generally reducing the difference between test and learning errors by a few percentage points. There are lots of other tricks of the trade, some written in the article dating back to 1998 that I wrote with Léon Bautou in a paper known as Efficient Backprop, and lots more in a work published edited by Montavon, Orr, and Müller, with lots of interesting techniques for deep learning. But it goes out of fashion rather quickly, this type of thing. Things go quickly. Let me explain how to create a neural network using a tool such as Torch. There are other tools like Keras and the like that use a similar syntax. So you create a sort of container in which you add modules that are linear or non-linear or pooling modules and so on. So a standard two-layer neural network with a softmax and a log softmax at the input and a negative input criterion due to cross entropy, as I said before. It's very easy to create a network and then to train it. I won't go into the details of this code. There are lots of tutorials available on using Torch and similar tools. But we have a loop that you need to predefine, calculating the cost function. You send it to an optimizer that carries an iteration. And the way you build this assessment value is what you will teach a mini batch to evaluate. It backpropagates, sends back the value of the cause function and its gradient with respect to a parameter. So it's a closure, in fact, for those of you who know what a closure is. And that is sent to the optimizer, and you send it, you iterate it, you send it to mini batches. It can be done in one page. Very simple. In 2 pages, you can specify a neural network and train it. It's extremely flexible. Torch is based on the Lua programming language, which is very simple, like Python, but far simpler. We have hash tables, also used as arrays and so on. So it uses Lua as the interface language. Behind it, it uses the best and fastest libraries for neural networks. Some parts are written in C or C++, and it's easy to interface them with Lua. And we have a large library, too, of calculations and for handling, manipulation, and computer vision. And lots of libraries to create convolutional networks, recurrent networks, and things of that sort. The system is primarily used for R&D in deep learning by Facebook, DeepMind, a subsidiary of Google in London, by Twitter too. The main developers of Torch work at Facebook, DeepMind, and Twitter. Of course, NYU and lots of other universities in Europe, the United States, and Canada, and lots of startups. I'm sure there are startup members here in Paris who use Torch. No one? Ah, there, at least 2. The main website is torch.ch. There's a large website with lots of resources on Torch. And if you don't like the idea of learning a new language, it's so simple that someone can write a page to teach you it in 15 minutes. It takes 15 minutes and no more. Well, that's what you need to understand the basics. Let's move on now to parameter transforms for deep networks. We can stack up boxes to create a network, but you can also have boxes that transform inputs into outputs, but also that transform parameters before they are used in functional boxes. Here is an example here. Let's say it's a conventional neural network controlled by a parameter vector W in a cost function, a classic. We transform the parameter space so that the parameters where we carry out optimization is a parameter U from which we can obtain W by transform G. All you have to do is backpropagate through this block as you would with any other block. So there's nothing complicated to create the system or to optimize it. I spoke about special examples. One example is parameter sharing. In this network, you can have several individual parameters, let's say weights, individual weights of several units in this neural network, and they must all take on the same value. The constraint is that all the points have the same value. So you'll have one parameter, one value that we distribute, share, in all the weights or connections that want to share this parameter. We saw the last time that this is just a block for doubling, a Y connection, sort of. We know that when you have a Y connection, sharing or distributing a value, when you carry out backpropagation, you need to sum up all these values to obtain the gradient with respect to the total parameter. So the gradient for a given U is a sum of gradients with respect to all the W's that are controlled by this particular U. I spoke about this because sharing parameters is something that is used in convolutional networks that I'll tell you more about in a few minutes. As a reminder, an example of an architecture that's becoming more and more used is now known as as an attention architecture. They emerged several decades ago in the context of what we call mixture of experts. Let's say you have one network with several outputs or several networks considered as experts on given sub-problems in a region of space. Let's say that this network recognizes a type of car amongst all cars, a type of truck here, a type of bike, but initially don't know if it's a bike, a truck, or a car. So here we have another network which decides if what you see at the input is a truck, a car, or a bike. But there are lots of things that are ambiguous. Sometimes you have cars that are big and they look like trucks, or a bike with 3 or 4 wheels that looks like a car. So you can decide a priori which expert will be in charge of each category. You leave that choice up to this other network, which is also trainable with trainable parameters. The output goes through a softmax, giving you values that are all positive, summing to 1. A sort of weighting, a coefficient of a means, let's say, and the ultimate output for the system will be the weighted sum of the outputs of each block. That can all be vectors, weighted by these weights. The sum is 1, so that calculates the weighted average. So it decides which expert will decide on the output. This is what we know as a mixture of experts. All you need is a model that tries to multiply vectors by scalar, one for softmax. This may be a neural network. It doesn't matter what you put inside. You train it with a gradient backpropagation without dealing with how the backpropagation of gradient works. It will deal with that itself, giving you a system that can direct the attention of the overall system to a given expert, to a given zone. This architecture is largely used today for problems with producing legends for images, or problems with automatic translation, where the input is a sentence that can be viewed as a sequence of vectors representing each word, and where they could look for the word in this target sentence. It calls for a mechanism that can enable the corresponding word in the input sentence. Let's say translating from French to English. The position of the verb will probably change a lot in the sentence. So when you need to produce the verb in the German sentence, it will probably be at the end, you need to look for the right word to be translated in the corresponding French sentence. We can use such mechanisms to choose the appropriate input. This type of architecture is also used a lot in what is known as memory-augmented networks. And it may be viewed as a sort of gating mechanism for a given memory box. And that was just in passing. And now let me move on to the origins of a convolutional network. Very often, you need to apply learning systems to signals that are not just feature vectors that are non-structured, but they may be sequences or arrays. 1 dimension, sequences, 2 dimensions, images, 3 dimensions, images or video, and so on. So this is in 1 dimension. We want to predict the time sequence. So we look at 3 values of a time series, and we try to predict the instant value of another sequence. Imagine that this, for example, is at random, let's say, currencies, values for currencies, or a financial instrument, and you want to predict should you buy or sell. So there is a simple technique that consists in using a sliding window on the signal. This system looks at a window of the signal, and it is trained to predict the value. Each example with a different window. That's a very natural idea. Lots of people use that in biocomputing to analyze biological sequences, or for language models that are built this way. Each word is represented by a vector, and you try to predict the next word in a text. It's very useful for handwriting or vocal recognition to see which word can follow a set of words, or to understand natural language and things of that sort. The big question is, what do you put in the box? Let us move on to the idea of convolutional networks. Instead of seeing this network as just one sample looking at a window, we try to look at several copies of this network at different moments. Here's a representation. Here we have a series of units looking at a neighborhood, two input variables on 3 time samples, each calculating the weighted figures. We have 3 units here with different weights that I did not draw. At the next moment, the same series of units, now looking at the following window, will carry the same operation, and this is repeated several times. We may imagine that to make this architecture deep, the next layer could take the results from this unit and the following moments and do the same thing, calculating a weighted average on the window to calculate the output. And at the next moment, you take, once again, the same window shifted by 1 notch. What's interesting here is that all these units at different moments are the same unit at different moments, so the parameters must be shared by them. This is the same as this with the same weights, giving us a network once unfolded where the weights are shared. This is why I spoke about sharing parameters before. This was just an introduction before speaking more explicitly about convolutional networks. As I said at the inaugural lecture, the idea is this. We want to build a hierarchical system and use the fact that patterns in an image, these are probably compositional, very much locally correlated, but not very much correlated at a long distance. And also the fact that we would like hierarchical systems that we observe in the visual system. In the visual system, neurons in the primary context area are connected to very local parts of the visual field. There are neurons in V1 that react to special edges at a specific part of the visual field, and that type of sensor is repeated throughout the visual field. So the same type of neuron looks at a different zone, but detecting the same pattern at several zones of the visual field. The idea of replicating a detector on the entire visual field is the same idea as translating a detector in time. If this array is bidimensional, you replicate these units throughout the surface. So replicating filters is a long-standing idea dating back not to Hubert and Riesel, who were people in neurosciences, but Fukushima, no relationship with the nuclear accident in Japan, maybe geographically. But at the time he did his research, he worked at the NHK Research Laboratory, the Japanese television company. He built a model that he called the neocognitron. In fact, it consisted in organizing the neurons, let's say, into planes, successive planes. Within a plane, all the neurons share the same weight, detecting the same pattern at different areas, each detecting a different pattern, followed by this one, followed by what we call complex cells. This is his term, and a term from Hubert and Wiesel. And these complex cells pool. Let me give you the details here. I started working with these models at the end of the 80s, when I was still doing my postdoctorate in Toronto, and then started running it at the end of 89. instead of 88 for handwriting recognition, the first system that could be trained end-to-end with pixels directly without feature extraction to recognize handwritten characters. This is a typical convolutional network dating back to that time, the end of the 80s, I believe in 1990. This was written by Nips in 1989. You take an input image, a bidimensional array, a pixel represented by 0 if white and 1 if black. We organize the first layer into planes, where each unit within a plane, the planes are known as feature maps. Each unit or each pixel in this plane will activate a specific unit on this plane. Let's take this white one. The result, it is the result of the scalar product of the values in the neighborhood with these weights. This is a representation of the weight's value. Black for positive, white for negative. We calculate the scalar product of this neighborhood with these weights, giving us this value after shifting to non-linearity. Here's a sigmoid. So we take this convolutional kernel, this small weight, that we slide on the input, and at each position we calculate the output corresponding value. The activations we see here are the outcome of this calculation of the scalar product, the weighted sum of these values by this weight for the entire neighborhood at the input. This operation is a discrete convolution from a mathematical perspective. This animation, I took it from Andrei Karpathy, a student at Stanford. He wrote this script. You can look at it on his website. He gave lectures at Stanford on convolutional networks. So you take this convolutional kernel, you calculate the scalar product with each neighborhood, and you write the output in the corresponding map. So a series of 3 planes. If you look at an image, a color image with 3 channels, red, green, and blue, these 3 planes could correspond to these 3 channels, red, green, blue. You apply the 3 convolutional networks, and you calculate their sum. And this is the sum that you write in the corresponding output. And you take 3 other convolutional networks, they work on the image, and you write the sum on yet another feature map. It's very easy, therefore, a linear operation that's easy to implement. Backpropagation through this operation is very simple, as I will show you. Now, to calculate backpropagation is the same thing as in a linear module, where we need to calculate the gradient by going to the matrix transpose or the linear operator in question. For backpropagation, you need reverse convolution. We take the convolutional network, you convolute with the output, you shift it to all the locations, if you wish, multiplied by these weights, you write the result here. It's exactly like a convolution, except that it's as if this image were the input image to which you added a 0 border, if you wish, and convolution is done with these convolution kernels and write the result of the output. And this is how you calculate the gradient. The values that you will use here to calculate the backpropagation gradient comes from the next layer. This is another example of a convolution network. The first layer, the result of 4 convolution kernels with the input. Each map detects a specific pattern. This one is enabled primarily for edges that go in this direction and not too much for vertical edges with very little activation. There's a sort of bipolarity of activation where a filter will be positively activated at a given location on an edge and negatively a bit staggered. So each filter does a different operation. And then we pool. The role of pooling consists in building a bit of invariance in the representation with respect to translation or distortions of the image. If you take a shape here and you transform it by translated by 2 pixels, this one too, because the calculation here is translation equivariant. In other words, the result is not changed when you translate the output, it must also be translated. But if you translate this by 2 pixels, this result will translate by 1 pixel. How? By sampling. You take the neighborhood of a unit here, 2 by 2s, you calculate the mean or the maximum, or the L2 norm, the square root or the Pn square root of the sum of values of the power P, something like that. And then you shift this window by 2 pixels. If you do that, this map will have a half of the resolution of this other map. If this map is 32 pixel high, this one will be 16 pixels. If you translate this by 1 pixel, this will be a half a pixel. By 2 pixel here, it will be by 1 pixel there. The result is that this operation eliminates a bit of information on the position of the features as they appear on the input. So you can distort the input slightly and slightly change the result of the representation. You repeat that process. It's like I explained the last time. First, you expand dimensionality in a nonlinear fashion, and then you pool, reducing dimensionality, putting together the semantically similar pieces. So the notion of semantic similarity is because forms that are slightly distorted with respect to each other are in actual fact the same object. If you're more into maths, wait for Stéphane Mallet's seminar. He'll give you lots of details. Here you repeat the same operation. This map, each value of this map is obtained by convolution with a convolutional net kernel 5 by 5 here on the previous map, but also combined with the other maps. So we have 6 convolutional kernels applied to these 6 maps simultaneously, then added, and then nonlinear to produce this one. Here, 6 other convolutional networks. And this is not from 6 to 16. It's one single set. Doesn't matter anyway. And then we have pooling and subsampling to reduce resolution once again. If this were translated by 2 pixels, this one will be by a half a pixel at the convolution, and so on. Here we get convolution. The vertical size of the kernel is the same as the input image, so the output image will only be 1 pixel high, several pixels wide. So each vertical section sees an input window, 32 by 32, shifted at the input. The idea is that as you get into the layers, you reduce the spatial resolution and you increase the number of type of feature maps, giving you a representation that's a bit delocalized. If you look once again at the part of the input that impacts a specific unit here at this level, you look at what impacts it. It's a 32 by 32 window, so it's relatively large. That's the architecture behind the convolutional network. Sometimes you normalize. Now there are several methods for normalizing. There is a very much used one that's called batch normalization. It's not on one individual sample, but the normalization coefficients are calculated on a mini-batch, hundreds of examples typically. I urge you to read that. You don't have to, though. You can just use the batch normalization module in Torch or in any other tool. So normalizing inputs, removing averages so that the values can have averages close to 0, normalizing variances, and so on. And then a filter band, which is exactly like in the convolutional kernel that you apply to an image producing feature maps. Nonlinearity, as point-by-point scalar, typically ReLU, this function, max of x0. And then pooling. Feature pooling. Typically, in the systems today, we have a max on a window, sometimes a max on several feature maps, pooling several feature maps into one. Depending on how you do this, some people call it max out. There are differences. Then an LP norm, you take each value that you'd like to add to the pool, v at the power p, then take the square root. And there are other pooling rules, like 1 and b, log sum exponential bx is the lump sum exponential that I spoke of the last time. This can be viewed as a sort of sum of probabilities in the log domain. That's the basic module that we repeat several times, and at the end the classifier is no different. It's just another filter band with linearity, nothing more. No clear distinction, therefore, between features extraction and classification. It's a continuum of scale. Here's how we create a convolutional network in Torch. You create a sequential module and you add a model, a spatial convolution model, hyperbolic, tangential, max pooling, and then we have fully connected layers to create this little architecture that we experimented with in the 90s for character recognition. We could give you details on how to calculate gradients in a convolutional layer, but this is all implemented in modules, so we don't have to deal with that any longer. It's quite simple to see how to do this anyway. There's an interesting feature in convolutional networks, because each operation is a convolution. In a way, these are networks of a variable geometry. If I take a window in an image, for example representing a character, or part of an image where you may have a full object, we can build a convolutional network taking this window, doing a convolution, pooling and so on, and coming up with a vector for classification. For example, a score for each class, so we can train it in a supervised manner with backpropagation, no problem. Now, very often, in image recognition, you don't just want to identify simple, isolated forms, but you'd like to recognize several objects in a large big image for face detection or for counting sheep. An example I showed you in the inaugural lecture, you would need that detector covering the entire image. A simple example for handwritten character recognition, a word may be formed of several characters, but you don't know where the characters are. One way to handle this is to take the convolutional network and to apply to all possible windows, and for each position at the input you record the corresponding outputs. You have a score for each character from A to Z in optical character recognition, and at each position where you have this convolutional network, you get a score telling you that it may be a C, in between it may be an I, and then you see a U, or maybe a W, and then an R. So you have lots of scores for each position for characters, and then you will need a post-treatment to try to extract the best interpretation of all these scores. But a very important feature of convolutional networks is you don't have to recalculate the entire network at each position. If you take the convolutional network on the left-hand side of this picture, it will correspond to a section of this, exactly of this size, and then you shift it by a few pixels to calculate the next output. A good part of the network has already been calculated. No need to recalculate. You just calculate the new section. When you assemble all the translated versions, from the input. All you have to do is to carry out the convolution on the entire input. Instead of doing the convolution on a small image and obtaining a small feature map at the output, you do a convolution the entire window, and you get the feature map, which brings together all the possible positions of these feature maps at all locations, and you do that for all layers. And you consider the last layer also as a convolution. So this convolution is applied at one location because that's all you have room for. But then it can be applied to all possible locations, giving you a series of outputs, each influenced by a different window at the input, shifted by a few numbers of pixels. The number by which this window is shifted corresponds to the product of the subsampling of all the layers within the network. Lots of advantages with this, so that a convolution network can recognize multiple objects like characters in a word, but also to detect objects in the context with a sliding window on a large image. So this is an example of how it can be used for character recognition dating back to the 90s. We trained a convolutional network, an individual one with just a 32 by 32 window. Here is 32 by 64. I cut off the edges so it's a bit less than 64. But theoretically 64. We trained a convolutional network with a 32 by 32 window to classify the 10 categories of characters. We also trained it to classify a character in the center in the presence of characters on the side, showing not just the character in the center but also other characters on the side to try to get the system accustomed to see characters on the side that may lead to confusion. We also train it in not classifying a shape in one of the 10 categories of characters. These are handwritten characters if the character is not properly centered in the image. We train it with characters that are not centered or with holes between the characters. We train the system to say that is neither a 0 nor a 1 nor a 2 nor a 9. So after training, we apply this convolutional network with this input that may vary in size. The only difference is that at the output, well, you have several outputs, in fact. What I'm showing here is the winning category with the highest score, and the gray level indicates the score in a way. Several of these detectors detect 5, 2 of them actually. And there are several detectors that identify 3. When both forms, shapes overlap, there's a little hesitation. And then, all of a sudden, it goes from 5-3 to 3-5 with a question mark in the middle. The advantage is that this shows that we can train a convolutional network to do recognition in context and not to be disturbed above all by surrounding shapes in the context, so that we do not have to do segmentation. Segmentation is a process that consists in detecting the object you want to recognize. You isolate it from its context and you present it to a classifier to represent the image. But it's as complicated as recognition. It can't be done properly without recognition. This type of training eliminates the need to do prior segmentation. Can we recognize several objects simultaneously? Here's another example I showed in the inaugural lecture, showing the system's ability to carry out feature binding. People in neurosciences were very much interested in this, to find what neural mechanism in the visual system made it possible to assemble edges or characteristics to form an object. So this is what is known as feature binding. It's just that you need a few layers with non-linearity, and it works on its own without any specific mechanism. Convolutional networks, what are they good for? They're good for signals that come in the form of arrays, multidimensional or single-dimensional arrays, different arrays, as a temporal signal, a sequence including text, voice, and so on. An image, a bidimensional table, or a time frequency representation for time series, for example, for audio. Images too, in color, multiband, multispectral images, 3D images, volumetric or video with a time dimension, and many other things. Tridimensional videos in tridimensional biomedical image analysis, for example. So everything that comes in the form of an array. Why is it that convolutional networks are good for this? It's because of natural data. In most natural data, in array form, we have a lot of local correlations. Variables in a small neighborhood are largely correlated in an image. There's a strong chance that two neighboring pixels in an image to have similar colors, unless there were an edge, which is relatively rare. So neighboring values are very much correlated, meaning that we can represent a neighborhood of pixels in a compact manner with a series of values, maybe with less than the number of pixels that you had, leading to the idea of local processing or local connections of detectors looking at a local patch of an image. And then we have the idea of translation and distortion and variance. If you have a small image distortion, you don't change the nature of the object. So you have the idea of pooling, eliminating the idea of position and features, so you can have a bit of invariance. Or, how would I put this? A bit of smoothness. Here's an example of an application that dates back to the days when I was at, well, dating back to the 90s. So at multiple scales, this convolutional network was trained to come up with this when a face was in its window. If you look at these maps at a large scale, the zone of influence of the size of the window is smaller than the faces, so the network comes up with just any old thing, not interesting. But at coarser scales, we can see clear detections of these two faces, and even coarser, a bit less. This dates back to a long time ago. More recently, we worked with Rita Osida. She's now in Israel. This was pre-done by Christophe Garcia, who was at France Telecom at the time, and now he's at the French National Institute of Applied Sciences in Lyon, and with Delakis on image detection with a convolutional network. I also showed you this during the inaugural lecture. And of course, applications of all this, not just for object detection, but for semantic segmentation and classification of regions or individual pixels. Here is an example. This study dates back about 10 years ago and a bit more on identifying particular zones in this image. This is in DIC, differential interference contrast microscopy, with an embryon that develops. We like to count the number of cytoplasm cells and so on to see if this animal is growing normally, developing normally. The carrier physiotypes in biology. So we train the network. It takes a large number of contexts and we clean up to be able to count the number of cells and kernels. A similar research, more recently, by Sebastian Song's laboratory at MIT, is now at Princeton, on identifying regions in 3D pictures for connectomics to be able to rebuild the neuronal circuit of a small part of a nerve. So convolutional networks have become a standard in biology for this. I also spoke about this at the inaugural lecture, semantic classification. This consists in classifying each pixel of an image with a category of the object to which it belongs. This dates back to a long time ago, between 2010 and 2012. The idea is to classify each pixel by a category, but without being able to decide the nature of a pixel without looking at the context. Here, if we look at a window, or a gray pixel here and one on the truck, a gray pixel in the sky and a gray pixel in the hair, or on the shirt of this person here, we need to look at a large context to determine the nature of these gray pixels. Is it the road, the shirt, the truck, or the sky? So the technique used here is a convolutional network, once again, looking at the same image at different scales. At a fine scale, the size of the input is 46 by 46 from the convolutional network, but with a sliding window. So it's a big convolutional network giving us 250 channels. And then a probability vector on probabilities for each window. The 46 by 46 window is not big enough to be able to decide on the nature of the central pixel. So apply the same network at coarser scales, a factor of 2, 4, going through the same convolutional network, the size adjusted to the size of the input. At the end, we bring all we bring them all to the same size, bringing them to the classifier for each input window. Each time you shift this window by 1 pixel, you wait a bit for this one. When this is shifted by 2 pixels, this is moved by 1 pixel. If you move this by 4 pixels, this is shifted by 1 pixel, and so on and so forth. By training the entire system from A to Z, we can obtain a system that classifies each pixel, and then we clean up with a process that I won't go into. We applied this to indoor images, and it works rather well. This is a video I also showed you at the inaugural lecture, and that I won't show again. So it works well. A lot of people have reused these techniques to apply them to bigger databases than what we had at the time. And now we have access to more efficient GPUs, or GPU codes that we have access to that are very efficient. This was the time when, well, this was published, let's say, in 2012. It was more precise than all competing systems on all 3 databases, about 100 times faster too. To give an idea about the sociology of sciences, there's something I find interesting. This article was rejected from the Vision conference, although it had a better performance and it was better in speed and precision. The thing is this: the reviewers of the article didn't have a clue about what the convolutional network was. They couldn't believe that the result could be so good using a technique that they hadn't heard of. Interesting things in sociology of sciences, and I'm sure that this will be enlightened later on. But there's a certain resistance that is natural. It's not to complain that I'm saying this, just to say that there's a natural resistance to new ideas, and you must be aware of that when you do sciences, including when you are a viewer and you read and criticize articles. It's very easy not to see the benefits of new ideas and not to understand what's behind an article. I was the program chair of this Congress some years ago, so I was in the opposite position before that. I'm not throwing stones at anyone, but this is something that you must try to make the most of. We can use this for piloting, steering robots, for driving cars, for object recognition, but I would like to show that we are seeing a major leap forward for convolutional networks. So modern convolutional nets have more and more layers. The two systems with the best results in ImageNet's contest and classifying objects in 2014 had either 20 layers, convolution, max pooling, convolution, max pooling, convolution, convolution, max pooling, convolution, convolution, max pooling, and so on. So these are fully connected layers. It's like a one-by-one convolution connection. This is a VGG network, the acronym referring to a laboratory at the University of Oxford that experimented with these architectures. That same year, a network proposed by Google known as GoogleNet. I don't know how to pronounce that. They're playing around with the name LeNet. My colleague gave that name to convolutional networks in the 90s using inception architecture, where a module that repeats itself, that you stack up, formed of several layers with varied convolution sizes that are all concatenated, pooled, and it is repeated several times, leading to a very deep network, but with very few parameters, and that was the advantage that Google was looking for to run these networks without taking up too much memory in their servers. The last competition by ImageNet and another competition called COCO, organized by Microsoft, led to this network called ResNet, produced by Microsoft Research Laboratory in Asia, in Beijing, with 152 layers. There's several variants with 30, 50, 100, 150 layers, with the idea that when you stack up layers, the problem is that gradients don't propagate well in the layers if a layer has weights close to zero. When you multiply gradients from the top by the transpose of this matrix, or by transpose filters if you wish, gradients become small, and as you backpropagate the gradients become smaller and smaller, and at the end you have nothing left, leading to difficulties with training very deep networks. The idea with ResNet is to have connections that jump, like sheep jumping. Identities equal to 1. They just copy this value 2 layers afterwards. There is a path for the gradient that can go through these connections without being deteriorated, if you wish. In actual fact, we can interpret the function of each small module as the identity function. All of these layers must have the same size, otherwise it doesn't work. The only place you can change is here, where there are no real identity connection, just a connection, just a standard linear trainable connection. So you can interpret the function for each small module as the identity function, which a nonlinear deviation carried out by the 2 layers that we leaped per connection, allowing us to train networks with a phenomenal number of layers. And it works extremely well. We don't know why, but it works extremely well indeed. I don't have a lot of time left, exactly 1 minute. We spoke about object detection, semantics, but I would just like to speak about one thing. Well, these are the slides that I will be presenting in a future lecture. Just one thing I'd like to point out. Today we use convolutional networks not just for image analysis, but also to produce images. This is something I speak about in the future when we speak about unsupervised learning in the last 2 lectures. Here's an interesting example I'd like to show to you in a way. Dosovitsky et al. Trained a convolutional network where the layers don't subsample, but upsample. We start from a layer which is a vector, you give it a spatial vector, a spatial dimension, via upsampling at each layer, a reverse convolutional network. The idea dates back to far. Let's say there was a paper by Patrick Simard and myself dating back to the beginning of the 90s using a similar idea for sequence generation to produce sequences of a trajectory. More recently, you have the deconvolutive network by my colleague at NYU who used this for a generative module for image recognition. But here it's really to produce images. They use a graphics engine with 3D models of a chair. They train the model to produce the image of a chair based on, let's say, the category of a chair. There's several possible categories, the viewpoint, and the transformation parameters, its orientation, scale, and so on. They train two independent convolution networks, one to produce a mask and the other to paint the chair with a mask. And it works very well indeed. At the end, by varying the values you enter, you can rotate the chair, calculate chairs that are sort of linear interpolation between several chairs, and vary orientation, size, and nonlinear parameters, and do arithmetics on chairs. So take an armchair, subtract another armchair, add a chair, and you have a chair that looks like the initial armchair. Another similar technique I will present in lectures on unsupervised learning. It's called adversary learning, which is even more amazing because we don't need to give any instantiation parameters. Here's another research by Kulkarni, building a sort of autoencoder. You put an image at the input, you go to the convolutional network. You give an idea of the instantiation values of the image. Let's say images of a face. You give the pose, elimination, identity of the person, and so on. So you train this network to transform the image into sensations, and another generative, giving another instantiation. And then we have an autoencoder that produces images that were interpolated amongst themselves. So I'll stop at that and give the floor to Stéphane. And thank you for your attention.